So we have defined what the limit of a sequence is. And today we would like to see some simple properties that will allow us to compute limits without having to go through the definition. Last time we did see examples using the definition of the limit, but in general, we should point out that it is quite desirable to be able to find limits without having to go through the definition, which is considered in most cases to be a cumbersome method. So to get started, let's just first note that there are some very simple properties that have to be proven, of course, but this is still not a proof-oriented course, and we're not going to attempt to give any proofs, but here they are. So suppose that the limit as n tends to infinity of the sequence an is L, and the limit as n tends to infinity of the sequence Bn is M. Then, first thing, the limit of the sum of the two sequences is the sum of the limits. So if you can look at the sequence and recognize it as the sum of two known sequences or sequences with known limits, then the limit of that sequence will be the sum of the limits. Same thing with the products. And in case that M is different from 0, the same thing can be said about the quotient of two sequences, that the limit of the quotient is the quotient of the limits. Now we should give some limits of some very simple sequences. So if an equals c is a constant sequence, so it just keeps taking the value c, then its limit is actually that constant value c. If then we would like to talk about two particular sequences. So the limit as n tends to infinity of n to the a is infinity if a is a positive number. And the limit as n tends to infinity of n to the a is 0 if a is a negative number. Of course, if a is 0, then you get the constant sequence 1, which of course has limit 1. So these are simple things that we can combine in different cases and come up with limits. And I should also say that there are statements regarding how to combine finite and infinite limits that in most cases they're quite straightforward, and we will see through some examples what we mean by that. So let's take a look at the following limit as an example. We will not attempt to do this limit by using the definition. Instead, we're going to do the following little trick. So, and this trick actually works for all limits of rational sequences. So I'm going to start with the limit. Please watch how I'm keeping the limit notation till the very end, when I can say what the limit is. So I factor out the largest power from each numerator and denominator separately. And in doing so, I just divide all the summands on the top by n squared. So this will give me 3 over n plus 2 over n squared And on the bottom, we'll get n squared times 3 plus 1 over n squared. Now, the thinking here is pretty straightforward. So first of all, these two things cancel each other. 3 over n, you have a power of n which is pretty much -1 times the number 3, so that will tend to 0. And this tends to 0. This tends to 0. This is a constant sequence that tends to 1. This is a constant sequence that tends to 3. So the whole thing, the whole numerator tends to 1. The whole denominator tends to 3. So simply speaking, the limit is 1/3. And that's it. And this is pretty much what we will do every time we have the quotient of two sequences that the quotient of two polynomials of n that have the same degree. Let's take a look at what will happen when we have that the degree of the numerator is greater than the degree of the denominator. So let's say that we have n cubed plus 7n squared plus 2 over 3n squared plus n plus 1. So we pretty much do argue the same way. So on the top, the highest degree is n cubed. We factor this out. On the bottom, it's n squared. We factor that out too. So here's what we get. N cubed times 1 plus 7 over n plus 2 over n cubed over n squared 3 plus 1 over n plus 1 over n squared. And now the crucial step is now we won't have a complete simplification as we had before. However, we'll have something else, which will be n cubed over n gives us n. And then we have the other fraction. For which we can argue pretty much the same way and assert that this whole thing tends to 1. Why? Because you have two terms that tend to 0. After all, this tends to 0 and this tends to 0, and 1 tends to 1. And this whole thing similarly tends to 3. So the whole thing here tends to 1/3, but then you multiply it by something that tends to infinity. So eventually the answer will be infinity, because think about it, you multiply really huge numbers, the ones that approach infinity, by numbers that tend to 1/3. The situation is even simpler if the degree of the denominator is greater than the degree of the numerator. So let's look at such an example. So let's say that we have the limit as n tends to infinity of n squared minus 3n plus 2 over n cubed plus n plus 1. Again, we use the same trick. We factor out n squared on the top. And on the bottom, we'll have 1 plus 1 over n squared plus 1 over n cubed. And now when we simplify it as much as possible, then what we're left with is 1 over n. And we have the other fraction. Where we have these 6 terms, 4 of which tend to 0. And the ones that do not tend to 0 are simply this one and that one, making the whole thing approaching 1. Yes, but 1 over n tends to 0. So the whole limit is going to be 0. And that's it. And we saw examples of all possible cases as far as the comparison of degrees is concerned for rational functions of n. Thanks for watching.